With all our concerns on Earth, space hazards like solar storms add to our worries, not just the economy. So what are solar storms? How do solar storms impact Earth's technology and communication systems? What measures can be taken to mitigate the effects of solar storms on satellites and power grids? Solar storms, also known as space weather events, are disturbances on the sun that release enormous amounts of energy into space. Number 1. Auroras, northern and southern lights. Auroras, known as the northern lights, aurora borealis, and southern lights, aurora australis, are stunning natural light displays in polar regions. These occur due to interactions between solar wind and Earth's magnetic field. The process starts with the sun emitting charged particles in the solar wind. When these particles reach Earth, they interact with our magnetic field, directing some particles towards the poles. There, they collide with atmospheric gases, exciting the atoms and causing them to emit light. The colors of auroras depend on the type of gas and altitude of the collision. Oxygen emits red light at higher altitudes and greenish yellow at lower altitudes, while nitrogen produces blue or purplish red light. These shifting lights create mesmerizing patterns. Auroras have significant cultural and historical impacts, inspiring various myths and legends among indigenous peoples. Scientifically, they offer insights into solar wind and Earth's magnetosphere, helping us understand space weather's impact on satellite communications and power grids. Number 2. Satellite damage. Satellites are crucial for modern life, supporting GPS, weather forecasting, and communications. However, they are vulnerable to solar activity, especially during solar flares and coronal mass ejections. Solar flares are sudden bursts of radiation from the sun, while CMEs release high-energy particles into space. When these particles hit satellites, they can cause immediate and long-term damage. High-energy particles can penetrate satellite shielding, damaging electronic components and causing malfunctions or permanent damage, such as data corruption from bit flips in memory. Solar activity can also affect satellite orbits. High solar activity heats the Earth's atmosphere, expanding it and increasing drag on satellites in low Earth orbit, causing them to lose altitude and re-enter the atmosphere prematurely. Historical incidents demonstrate the risks. The 2003 Halloween storms caused anomalies in over 47 satellites, including the loss of Japan's Aetios 2 satellite. In 2012, a powerful CME narrowly missed Earth, potentially avoiding widespread satellite failures. Number 3. Power grid failures. Solar activity can severely disrupt power grids through geomagnetic storms caused by solar flares and coronal mass ejections. These storms induce geomagnetically induced currents that can damage electrical infrastructure. When CMEs or solar flares reach Earth, they cause magnetic field fluctuations that induce GICs in power lines. Transformers are particularly vulnerable, as these currents can cause overheating and failure. A few key transformer failures can lead to widespread blackouts. A notable example is the March 1989 geomagnetic storm, which collapsed the Hydro-Quebec power grid in Canada, affecting over 6 million people for 9 hours. Modern reliance on electricity means such failures can disrupt critical services like hospitals, water supply, and communication systems. Number 4. GPS disruptions. Solar activity can disrupt GPS systems essential for navigation in aviation, shipping, and personal use. GPS signals travel through the ionosphere, which can be disturbed by solar flares and coronal mass ejections, leading to signal degradation or loss. Solar flares release bursts of radiation, causing ionospheric changes that delay or alter GPS signals, resulting in positioning errors. For instance, a strong solar flare in 2006 caused GPS disruption, leading to positioning errors of several meters. CMEs can create geomagnetic storms that further disturb the ionosphere, prolonging GPS signal degradation. Number 5. Radio communication blackouts. Solar activity can disrupt high-frequency radio communications vital for aviation, maritime, military, and emergency services. Solar flares emit bursts of ultraviolet and X-ray radiation that increase ionization in the ionosphere, absorbing or reflecting HF radio waves and causing radio blackouts. An example is the October 28, 2003 solar flare that caused a widespread radio blackout, affecting aviation communication over the Atlantic Ocean. Pilots and air traffic controllers faced significant communication difficulties, crucial for safe navigation. Number 6. Increased radiation exposure. Solar activity increases radiation levels in Earth's atmosphere, posing risks to passengers and crew on high-altitude flights and astronauts in space. This increased radiation comes from high-energy particles emitted during solar flares and coronal mass ejections. These particles can reach Earth within minutes to hours, generating secondary radiation that penetrates aircraft and spacecraft. High-altitude flights, especially on polar routes, are more exposed due to weaker magnetic field protection at the poles. Increased radiation can exceed safety limits, raising health risks like cancer and other radiation-induced illnesses. Number 7. Pipeline corrosion. Solar activity can cause pipeline corrosion through geomagnetically induced currents during geomagnetic storms. These storms, triggered by solar flares and coronal mass ejections, induce electric currents in long metal structures like pipelines, leading to stray current corrosion. When CMEs or flares interact with Earth's magnetosphere, they cause magnetic field fluctuations that induce GICs. These currents accelerate electrochemical reactions, degrading pipeline metal and increasing corrosion rates, potentially causing leaks or failures. A notable incident was the 1989 geomagnetic storm, which increased GICs in North American pipelines, raising corrosion concerns. Pipeline leaks can lead to environmental disasters and pose safety risks to nearby communities. Number 8. Animal navigation issues. Solar activity can affect animals that use Earth's magnetic field for navigation, such as birds, bees, sea turtles, and whales. These animals rely on magnetoreception to detect the magnetic field and orient themselves during migrations. Solar flares and coronal mass ejections can disrupt the magnetic field, causing temporary disorientation in these animals. Changes in the magnetic field can confuse their navigation, leading to difficulties in finding their way. For example, migratory birds may deviate from their paths, leading to increased mortality or reduced breeding success. Sea turtles, which use magnetic cues to return to nesting sites, may struggle to find their way, affecting population dynamics. Number 9. Internet disruptions. Solar activity can disrupt internet infrastructure, particularly undersea cables and satellite communications. Geomagnetically induced currents from geomagnetic storms can affect repeaters in undersea cables, causing malfunctions or failures. Undersea cables are critical for global internet connectivity, carrying data between continents. While cables are well shielded, repeaters are vulnerable to GICs, potentially leading to significant data transmission disruptions. Satellite communications are also at risk. Solar flares and coronal mass ejections produce radiation and energetic particles that interfere with satellite electronics. Severe events can damage satellites, affecting internet services. Number 10. Climate impact. Solar activity influences Earth's climate primarily through variations in solar radiation and the sunspot cycle. These variations affect the amount of solar energy reaching Earth, impacting temperatures and weather patterns. The sunspot cycle, which lasts about 11 years, involves periods of high and low solar activity. During high activity, increased solar radiation can slightly warm the Earth's surface, while low activity periods can contribute to slight cooling. Historical data suggest correlations between prolonged periods of low sunspot activity, like the Maunder minimum, 1645 to 1715, and cooler climate periods such as the Little Ice Age. Solar activity also affects the ozone layer. Solar ultraviolet radiation plays a key role in ozone production and destruction. Increased solar UV during high activity periods can lead to higher ozone concentrations, influencing atmospheric temperature and circulation patterns. So, this seems enough for today's video. Thanks for watching, and stay tuned for more.